When dealing with underground circuits that fail a Megger test, especially after replacing the conductors, it's crucial to systematically investigate the issue. Approving the energization of cables without proper testing is strongly discouraged due to significant safety risks. The first step is to verify the Megger testing procedure itself. Ensure the testing equipment is calibrated and used correctly. Consult the manufacturer's instructions for proper test parameters, voltage levels, and duration of the test. Confirm that the connections are clean and secure to avoid false readings. Next, a detailed physical inspection of the cables is essential. Look for any cuts, nicks, abrasions, or signs of physical damage that could allow moisture to penetrate the insulation. Consider using a visual inspection method such as a bristle to examine the cable surface more closely, especially in areas that are difficult to access. Ground fault locators can also help identify potential insulation defects. If physical damage is suspected but not immediately visible, more advanced testing methods might be needed. Consider performing a very low frequency, or VLF, dielectric test. This test uses a low voltage, typically 1 to 5 kV, and a higher frequency, around 0.1 to 1 Hz. The VLF test is often less affected by moisture compared to traditional Megger tests and can provide a more accurate assessment of the cable insulation integrity in wet conditions. It's important to understand that the presence of moisture can significantly impact Megger test results. While modern cables are designed to be water-resistant, prolonged exposure to water, especially in locations with a high water table, can lead to moisture ingress over time. If moisture is suspected, try to determine the extent of the problem. A fault locator can pinpoint the location of any insulation defects or potential moisture ingress points. This narrows down the problem area for further investigation and repair. If you suspect moisture is trapped in the cable surface, try applying heat to the cable using a heat gun or heat blanket. Maintain the temperature below the rated insulation temperature of the cable to prevent damage. The goal is to gently dry out any surface moisture that might be affecting the insulation resistance. Once the area is dried, retest the cable to see if the Megger reading improves. If moisture ingress is confirmed, applying a moisture sealant to the cable connections in any exposed areas helps prevent future infiltration. Ensure the sealant is compatible with the cable insulation material and follow the manufacturer's instructions for proper application. After any repairs or treatments, it's crucial to retest the cables regularly using a Megger to monitor the insulation resistance. This helps assess the effectiveness of the corrective measures and identify any potential issues early on. The acceptable Megger test values vary depending on the cable type, voltage rating, and length. Consult industry standards and manufacturer's specifications for guidance on acceptable insulation resistance levels. It is important to remember that powering up cables that have failed a Megger test is strongly discouraged. The damaged insulation can lead to electrical incidents, including short circuits, ground faults, and even fires. The contractor should conduct further troubleshooting and take appropriate corrective actions to resolve the insulation issues before the circuits are energized. If the troubleshooting process becomes complex, or you are unsure about the best course of action, consider involving an independent electrical testing laboratory or a qualified electrical engineer. They can provide an independent assessment of the situation and recommend solutions tailored to the specific circumstances. The engineer may also suggest performing additional tests, such as partial discharge testing, to evaluate the condition of the cable insulation more thoroughly. Partial discharge testing can detect subtle insulation defects that might not be apparent during a standard Megger test. In addition to the testing and repair procedures, consider the overall design and installation practices to prevent future problems. Ensure that the underground cables are properly installed in accordance with industry standards and local electrical codes. Proper cable bedding, backfilling, and trench drainage can help minimize the risk of moisture ingress and physical damage. Also, consider using cable with enhanced moisture resistance properties, especially in areas with high water tables. When splicing or terminating cables, always use approved connectors and follow the manufacturer's instructions carefully. Improper connections can create points of weakness that are susceptible to moisture ingress and corrosion. Regularly inspect the manholes and underground vaults where the cables are located. Look for signs of water accumulation, corrosion, or physical damage. Implement a preventative maintenance program that includes periodic Megger testing and visual inspections to identify and address potential problems before they lead to failures. Document all testing and repair activities thoroughly. Keep records of Megger test results, VLF test data, fault location reports, and any corrective actions taken. This information can be valuable for tracking the condition of the cables over time and identifying trends that might indicate potential problems. The original attempt to dry the cables by applying 120 volts is generally not recommended. This method is unlikely to be effective and can potentially damage the cable insulation. Applying excessive voltage to wet or damaged insulation can accelerate the degradation process and lead to premature failure. Instead, focus on identifying and addressing the root cause of the moisture problem using the methods described earlier. Remember that the primary goal is to ensure the safety and reliability of the electrical system. Do not compromise on testing and repair procedures in an attempt to expedite the process. Taking the time to properly troubleshoot and address the issues will ultimately save time and money in the long run by preventing costly failures and potential safety hazards. Let's delve deeper into some specific aspects of cable testing and troubleshooting. When performing a Megger test, pay close attention to the polarization index, or pi, and the dielectric absorption ratio, or DAR. These ratios provide additional insights into the condition of the cable insulation. The polarization index is the ratio of the insulation resistance measured after 10 minutes to the insulation resistance measured after 1 minute. A high polarization index, typically greater than 2, indicates good insulation quality. A low polarization index, less than 1, suggests that the insulation may be contaminated with moisture or other contaminants. The dielectric absorption ratio is the ratio of the insulation resistance measured after 60 seconds to the insulation resistance measured after 15 seconds. The dielectric absorption ratio provides information about the absorption characteristics of the insulation. Like the polarization index, a low dielectric absorption ratio can indicate insulation problems. When interpreting Megger test results, it is important to consider the temperature of the cable. Insulation resistance decreases as temperature increases. Therefore, it is essential to correct the Megger readings for temperature to ensure accurate assessment. Consult industry standards and manufacturer specifications for temperature correction factors. If the cable is known to be wet, consider using a direct current high potential or DC high pot test instead of a Megger test. A DC high pot test applies a high voltage direct current to the cable and measures the leakage current. The leakage current provides an indication of the insulation integrity. The DC high pot test is less sensitive to moisture than a Megger test and can provide more reliable results in wet conditions. However, it is important to use caution when performing a DC high pot test, as it can potentially damage the cable insulation if not performed correctly. Follow industry standards and manufacturers' instructions carefully. The use of a surge arrestor is vital to protect electrical equipment from overvoltages caused by lightning strikes or switching surges. Overvoltages can damage cable insulation and lead to premature failure. Install surge arrestors at appropriate locations along the cable run to divert overvoltages to ground. Ensure that the surge arrestors are properly grounded and maintained. Proper grounding is essential for the safe and reliable operation of electrical systems. Grounding provides a low impedance path for fault currents to return to the source, minimizing the risk of electrical shock and equipment damage. Ensure that all cable shields, metallic conduits, and enclosures are properly grounded in accordance with industry standards and local electrical codes. Regularly inspect the grounding system to ensure that it is in good condition. Cathodic protection can be used to prevent corrosion of underground cables and metallic components. Cathodic protection involves applying a direct current to the metal structure, making it the cathode in an electrochemical cell. This prevents the metal from corroding. There are two main types of cathodic protection systems: firstly, impressed current systems, and secondly, galvanic anode systems. Impressed current systems use an external power supply to provide the direct current. Galvanic anode systems use sacrificial anodes made of a more reactive metal to provide the direct current. Select the appropriate type of cathodic protection system based on the specific conditions. Regular maintenance is critical for ensuring the long-term reliability of underground cable systems. Implement a comprehensive maintenance program that includes periodic inspections, testing, and repairs. The maintenance program should be tailored to the specific conditions and requirements of the system. Keep detailed records of all maintenance activities. The use of proper cable lubricants during installation is essential for minimizing friction and preventing damage to the cable insulation. Select a cable lubricant that is compatible with the cable insulation material and follow the manufacturer's instructions for proper application. Avoid using excessive amounts of lubricant, as this can attract dirt and debris. Cable pulling tension should be carefully controlled during installation to prevent damage to the cable. Use a cable pulling dynamometer to monitor the pulling tension and ensure that it remains within the manufacturer's recommended limits. Avoid exceeding the maximum pulling tension, as this can damage the cable insulation and conductors. When backfilling trenches, use proper backfill materials that are free of sharp rocks and debris. Sharp rocks can damage the cable insulation and lead to premature failure. Compact the backfill materials properly to provide adequate support for the cable. Avoid using heavy equipment to compact the backfill directly over the cable. If multiple cables are installed in the same trench, maintain adequate spacing between the cables to prevent overheating. The National Electrical Code, or NEC, provides guidelines for cable spacing in underground installations. Overheating can degrade the cable insulation and reduce its lifespan. Cable identification is crucial for facilitating maintenance and troubleshooting. Label all cables clearly and permanently at both ends and at intermediate points along the cable run. Use cable markers that are resistant to weathering and corrosion. Keep an accurate record of the cable identification scheme. Avoid bending cables excessively, as this can damage the cable insulation and conductors. Use proper bending techniques and equipment to ensure that the cable is not bent beyond its minimum bending radius. The minimum bending radius is specified by the cable manufacturer. When splicing cables, use approved splicing kits and follow the manufacturer's instructions carefully. Improper splices can create points of weakness that are susceptible to moisture ingress and corrosion. Ensure that the splice is properly sealed to prevent moisture from entering. Cable termination should be properly installed and sealed to prevent moisture ingress and corrosion. Use approved termination kits and follow the manufacturer's instructions carefully. Ensure that the termination is properly supported to prevent strain on the cable. When working on underground cable systems, always follow proper safety procedures to prevent electrical shock and other hazards. Wear appropriate personal protective equipment, or PPE, including insulated gloves, safety glasses, and hard hats. De-energize and ground the cable before working on it. Use a voltage tester to verify that the cable is de-energized. Follow lockout/tagout procedures to prevent accidental re-energization of the cable. Be aware of the potential for hazardous gases in underground vaults and manholes. Use a gas detector to monitor the atmosphere before entering the vault or manhole. Ventilate the area if necessary. In summary, dealing with underground cable failures requires a systematic approach that combines thorough testing, careful inspection, and adherence to industry best practices. By following these guidelines, you can identify and address the root causes of the failures, ensuring the long-term reliability and safety of the electrical system. Consulting with qualified professionals, such as electrical engineers and testing laboratories, can provide valuable expertise and support throughout the process.